very first quantum computing event. At SGInnovate, we believe Singapore has the capabilities and resources to tackle hard problems from around the world, and part of our efforts includes knowledge-sharing sessions like the one today. Without further ado, I'll pass the mic on to Jenny, who will start us off. Jenny, please.
Okay, good evening, everybody, and thank you for being here. Thank you, SGInnovate, for making this event possible. So tonight, we're talking about the present and future of quantum computing. So my name is Jenny. I manage outreach at the Center for Quantum Technologies here in Singapore, and I'm moderating for you tonight. So we're going to start with an introduction to quantum computing. You're all here, so we assume you're interested in the topic, and I can see in the audience that we do have experts, but we're not going to assume that everybody knows this subject inside out. So maybe you have just read in the news about the new flagship that's worth €1 billion in Europe, or perhaps you heard about Singapore's quantum engineering program, or maybe you've read in the New York Times or The Economist, or maybe soon in the Straits Times about all the startups that are coming up in this field. So if you need to get the science behind the stories, we're going to start with a gentle introduction by my colleague, Dr. Joe Fitzsimons from the Center for Quantum Technologies. Now, if you are an expert, we have a panel coming later with representatives from local companies and industry who'll be able to take even your most detailed questions, so please save those up for then. Joe trained as a theoretical physicist and works on quantum computing. He has a particular interest in using quantum phenomena for secure quantum computing. And he's an associate professor at Singapore University of Technology and Design, as well as being a principal investigator at CQT. So as of last year, he's also the co-founder of an early-stage startup in Singapore called Horizon Quantum Computing. So, Joe, over to you.
Thanks very much. So maybe I should come over here to be within Bluetooth range of the laptop. Okay, so I want to give you a very broad idea of where things are at in quantum computing. It may be that you already know much more than is in the slides, in which case I apologize, and you can grill us on more detailed questions when we get to the panel discussion. And I'm going to give everything kind of in the form of these cartoons, which my wife helpfully drew for me. It's also in this kind of sketchy cartoon way so that you don't take anything I say too seriously. Because it's all going to be a fairly high level, and we're not really at the stage of having large-scale quantum computers at the moment. But I'll tell you a little bit about where things currently are and what the challenges are going forward. So if you think about how your computer works, at a kind of abstract level, what it's doing is very similar to what you do when you work with a pencil and paper. So it's basically retrieving some information from memory. So if you're working with a pen and paper, that's like looking at a symbol you've written down somewhere else on the page. And then that's determining what it's going to write down for the next symbol, and it's going back and forth between these two. So it's just retrieving something from memory, making a simple manipulation to it, and recording the result, and repeating this over and over again, using only simple rules to update it each time. And that's generally what any kind of computer that you're used to does. Sometimes there'll be parallel processing, like in a graphics card, which is the same as having a couple of people working with a couple of different pieces of paper that they keep sharing around one another. But ultimately, it's pretty much equivalent to working with a pen and paper. But this model of computation doesn't capture anything. So it doesn't capture everything. So we use this idea of recording symbols on paper or on some kind of tape and making a simple manipulation of them and then recording the result. We use this to formalize the general model of computation, of conventional computing, in something called a Turing machine. So a Turing machine is really literally doing precisely what you do when you're working with a pen and paper. But there's a couple of things it doesn't capture. There's a few areas of modern physics that aren't captured by this. In particular, there's quantum mechanics and there's general relativity. And both of these were discovered kind of post-1900, and they've brought about big changes in physics, but they haven't made their way into this notion of computation until more recently. So one of the reasons this kind of changes your model of computation is because if you think about what you can do with a pen and paper, the states you write down, you can tell the difference one from the next. You can't write down quantum states, for example. And you don't have access to kind of exotic space-time like having a time machine or something like that. Because it turns out if you have a time machine, that can really impact the performance of your computer because you can keep going back in time with it. But realistically, we don't think you get very much of a speed up from relativity unless you have access to really exotic space-times like time machines. You know, if you want to be taken seriously as a physicist, you don't call them time machines, you call them closed time-like curves. But they're something that people have actually spent a fair amount of time studying. If you have them, then it maybe helps computation, but we have no idea whether that's possible. Probably it isn't. I don't think anyone really believes it's possible. And it's certainly not something we can do in a lab. So that kind of rules out building in general relativity into our computers. But quantum physics, we've actually gotten pretty good at. We're fairly good at manipulating quantum systems in the lab, and it's getting to the point where you can start to use them to process information. So instead of writing down your information as ones and zeros either on a piece of paper or on the surface of a magnetic platter on a hard disk, or in an array of NAND gates and flip-flops in a computer memory, instead you might think, well, maybe I will prepare an ion or an electron or something in the state to be 1 or 0. And if you go down this route, it leads to the idea of quantum computation. And you can record things as quantum states rather than as these definite things that can either be 1 or 0. So this allows you access to quantum phenomena of superposition and entanglement, which it turns out has a big effect on the computing model. So this gets you to the idea of a quantum computer. What a quantum computer is, it's basically recording, storing, and manipulating information as quantum states rather than as classical states that can be distinguished from one another. Quantum states, you can't always distinguish them from one another, which is useful for cryptography, but you also get interference effects, kind of wave-like interference, which is really useful for algorithms. And actually, if you kind of start enumerating the different applications, you find that there's kind of 4 broad classes of applications for quantum information processing. So that's just processing information stored in quantum states. The one I'm going to focus on mostly is on algorithms, so making better computers and making better algorithms to run on those computers. But there are also advances for security. You can make more secure crypto systems than you can otherwise. You can also achieve computation of certain kinds of distributed functions more efficiently than you could using conventional computers. So that even if the time they take to compute some function is the same, the amount of bandwidth they use is less. And also use in sensing. So you can use quantum states to make more precise measurements of their environment than you can without making use of quantum mechanics. So you can build some of the most sensitive sensors using quantum techniques, quantum information processing techniques. So I'm going to focus mostly on algorithms and on, I'll talk a little bit about security. Oh, sorry. Okay, so I mentioned qubits. And this is an important measure for any quantum computer. And it's basically, the qubit is basically an equivalent of a classical bit. So in your computer, all of the information is stored in bits. They're kind of the most basic unit of information you can have, just a 1 or a 0. A qubit is a quantum equivalent of this. It has 2 distinguishable states. So there are 2 states that you can tell apart from each other with 100% certainty. But it can also exist in any superposition of these 2 states. And this is just a kind of quantum phenomenon. It's a bit like a probability distribution. But it has the effect that these amplitudes, they're called, that are associated with the 2 distinguishable states can be both positive and negative. And this is important in achieving interference in the computation, to have these kind of wave-like interference effects. And without those, there's no computational advantage. So you really need to make use of them if you want to get any kind of advantage in your quantum computer. Now, you could say, well, why can't I just simulate a quantum computer? Why do I need to bother making some hardware device? Why don't I just try to record what the state would be? Physics is basically deterministic. So if you know the state of the system at a particular time, and you know all of the forces and fields affecting it, then you can work out what the state of the system is going to be at a later time. So why don't you just use your laptop to do that? And the reason for this is basically that the state you have to simulate requires an awful lot of processing power or an awful lot of memory. So the state you need to record ends up being exponentially large. So you need to really use an exponential amount of memory. So in order to record the state of 50 qubits here, so 50 spins, actually this might be 49. So if I want to write down a general state of that system, I'm going to have to write down 2 to the power of 50 real numbers, and that's a really large number. Okay, so each power of 2 to the 10 is about a factor of 1,000. So if you have 50 of these, it's about a million billions. So it's really quite a large number. And so you rapidly run out of memory in your device if you try to record the state of the system. There are some other approaches that try to bypass this. And you can kind of trade processing power for memory in some cases. But ultimately, it just takes far more processing time to simulate the system than it does to actually implement it in hardware. And that's ultimately what people are trying to do with building a quantum computer. You're trying to build a hardware system that is governed by quantum mechanics in such a way that you cannot simulate it efficiently on a conventional computer. And we know that once you hit around 50 qubits, if the noise level is low enough and if the operations you're doing on them are precise enough, then you can start to solve certain problems, maybe not very useful problems, but certain random problems that you cannot solve on a conventional computer without spending a huge amount of time on it. So this is sometimes called quantum computational supremacy. And we're starting to get kind of close to this threshold now, which is adding a lot of fuel to the field at the moment and adding a lot of excitement to the field. So when I started off around 2004, the maximum number of qubits in any device in the world was around 8. So that was about the largest system that had ever been built. And 8 qubits, you do not need a large computer to simulate. If you have a lot of time on your hands, you could simulate it by hand and work it out by multiplying 8 by 8 matrices together. But it's kind of trivial to simulate on a cell phone or something like that. Even 20 qubits is kind of trivial to simulate on a cell phone. But since then, it's kind of plateaued. So it was looking fairly good. It was kind of going uphill, and then the number of qubits stagnated. So it went from about 8 to about 14 qubits over a span of about 10 years. And that's not fantastic. If we want to see large devices with maybe millions or billions of qubits, that's not looking great. But what's kind of led to a lot of excitement in recent years is that there's been a big uptick in this. So the number of qubits in devices has shot up. And so this is kind of, not all of these devices are publicly available or necessarily known to actually really exist, but this is kind of based on, some of these are based on announcements. Actually, if it's based on announcements, it's like somewhere up here now. But this is kind of cause for some interest. And you might ask, why is this the case? It turns out if you plot all of the bumps on this curve, you get a fairly good quantum Moore's law. But the doubling time isn't 18 months, like with conventional semiconductor technology for the number of qubits, so basically the amount of memory. It's instead about 5 years. And that's why it's really slow growth. Right? So you could say, well, it's completely consistent with exponential growth, it's just really, really slow. But you could say, well, why do you have this big uptick at the end? And that's because something important happened around 2012. So around 2012, for the first time, it was shown that you could manipulate qubits with a good enough level of accuracy that maybe you would be able to correct errors as they occur. Maybe you could do error correction, active error correction in your device to start to suppress errors as they began to build up in the device. So this means that the level of noise in your device, you could always keep a hold on it. If you're above this threshold, the errors kind of run away with themselves and you get garbage out after a long computation. But if your operations are accurate enough that you can implement active error correction during the computation, then you start to be able to store information for a longer amount of time. You start to be able to do larger computations. And while we haven't actually really seen demonstrations of this in practice yet, it has been the case that basically a lot of people working on these systems have shifted from trying to make better qubits to trying to make more qubits of more or less the same quality. Perhaps a little bit better, but the effort seems to have shifted more towards more rather than better qubits. In this time, the quality of the qubits actually improved tremendously. So there was something, so if you look at the last 2 years or so, you get a doubling time, but it's not what it was before. It's not 5 years. Now it's down to something that's more like 6 months, which is kind of interesting, and it gives maybe some reason to be hopeful that we'll be able to see large enough devices with enough qubits, and hopefully that they'll maintain high enough quality that you'll start to be able to do something that's interesting. So we need to get from whatever 20 qubits or whatever the best is currently at the moment to 50 qubits or more to see an advantage. And there's some hope that we'll see that perhaps this year or early next year. And then kind of longer term, we need to get to a point where there's active error correction in the system. And that's still some way off. But hopefully we'll start to see demonstrations of that in the coming years. During that time, when I said there had been this kind of very slow growth in the number of qubits, something that really improved a lot was the quality of the qubits. So this plot's just for superconducting qubits. And basically what it is the doubling time for the amount of time you could leave a qubit on its own before an error occurred. So this is called the coherence time of a qubit. And so in the late 90s, it was about a nanosecond for superconducting qubits. And it's gone up by about 5 orders of magnitude since then. So the doubling time for that is more like 1 year, maybe even less than a year. And that's been pretty consistent for about 20 years as well. So the quality of the qubits has really improved. And so they're now getting to a point where maybe they'll start to be useful for computation in larger devices. But it's important to keep in mind that the quantum processors we have now, so this is just kind of a sketchy version of a Dill fridge, I guess with IBM on it, because they have this system. But if you, the systems we have now, the quality of the qubits in them is still not the same as the quality of the bits in your laptop, right? If you record something on your hard disk, the chance of it encountering an error is really small. I think it's like 10 to the minus 18. So it's something like 1 in a billion billions that a bit in your hard drive will go wrong. And if you work on high-performance computing, that's an important thing to keep in mind, because you might be doing a huge amount of computation, and so that chance might actually affect things. But for a regular laptop, it doesn't matter. So you don't need to care about error correction. On current devices, errors occur more like 1% of the time or 5% of the time, or something like this. The error correction threshold is about 1% for the codes people like to use. For codes people don't like to use because they're very inefficient, it's more like 3%. And so if you get the rate of errors down below this, then you can start to hopefully actively error correct things. So really these devices are much like the very first computers. It's not an equivalent of your laptop, it's an equivalent of ENIAC or something like that. Okay, so if you kind of buy into this, that these are real devices that have some future, you can say, well, what are the applications? And at the moment, until recently, the key applications have been things like cryptanalysis. So this is one of the very first things that were discovered, that you could break codes with it. You can break RSA. You can break elliptic curve crypto systems very efficiently with it. You still need a fairly large quantum computer, thousands of qubits without error correction, and if you add in error correction, then that number blows up to millions. But there's also things like simulation, so simulating chemistry, simulating quantum materials, simulating condensed matter systems, so things like optimization. And then there's computing various mathematical functions. Things like, so there's knot invariance. So in knot theory, there are these polynomials that you can assign to a particular way of braiding ropes. And you can compute things like that with your quantum computer. And more recently, it's been realized that they're also really useful potentially for machine learning, because they're very good at fast linear algebra. So they can do fast matrix multiplication and matrix inversion and things like this. So you can kind of look at the timeline. This has gone from the, say, the mid-90s up until pretty close to the present, and you can say, why so few algorithms? And, you know, I've been a bit disingenuous. Not all of the algorithms are here. There are a bunch more algorithms. But this is fairly representative of the types of algorithms we have. And there's a couple of reasons algorithms are hard. One of them is that we just don't have an intuition for it. So if you lost your keys, say in some room, one of the offices in this building, but you didn't remember which office it was, and you didn't remember even vaguely where it was, the algorithm you would come up to find them is something like, I'm just going to try each office in order. Or I'm going to start with the office I think was most likely to have left them, and I'll just keep trying in descending order until I find my keys. And that's pretty much the best algorithm you can have, right, on a classical system. That works, but it takes you some time that scales linearly with the number of offices in the building. But it's very natural. It's easy to come up with that algorithm. Didn't take much effort to come up with it. But the best quantum algorithm is very different. You try all of the offices in superposition, you come back to a single point, you harness a fairly complex interference effect, and then you repeat the process over and over again, and the number of times you have to repeat it scales as the square root of the number of offices. So you can search more efficiently, significantly more efficiently on a quantum computer, but reaching that conclusion is not so easy. It's not something that you would naturally come up with because it's not something you can do in practice. We don't really have experience of making use of these interference effects in practice. Another problem is just that not very many people work on this. So if you try to estimate the number of people that work on quantum algorithms, I've tried myself and I've asked a bunch of other people that work in the area on Twitter, and it seems like the best we can come up with is it's some number under 200. And if you look at the number of people that are writing software for conventional computing, that number is higher. So you can estimate it perhaps by the number of active GitHub accounts, and that's well over 50 million. So there's a real discrepancy in the numbers of people working on conventional computing problems versus people working on quantum computing problems. Now, you could say, what about the number of people that actually have played around with a quantum processor, like on the IBM system, and that number is much higher. But the number of people that actually have novel results that are published in papers and that are generating maybe more than one paper over their career so far, that number's low. But you can take some inspiration and you can look at this timeline. You can kind of fill out the timeline of advances in quantum computing, and you can fill out the timeline of advances in classical computing between about 1940 and 1960, and basically almost everything in the advancement of quantum computing has a direct analog in the advancement of classical computing, of just conventional computers, between around 1940 and 1960. So you've got search algorithms, which are roughly equivalent to the sorting algorithms of the early 40s. You've got factorization algorithms, which is like this cryptanalysis one, and some of the first uses of computers were to break Enigma and other codes during the Second World War. You have optimization algorithms, and the simplex algorithm, which is a very well-known optimization algorithm, was discovered in 1947. Even machine learning. So I mentioned machine learning as something pretty recent that quantum computers are turning out to be good at. But actually, there's a lot of noise about deep learning now. But if I ask you when neural nets were come up with first, would you have any idea? It turns out it was in 1943. So the first paper introducing them, the McCullough-Pitts artificial neuron, was introduced in 1943. So there's really a direct analog between what's gone on in the recent history of quantum computing and kind of the very early history of classical computing. So it's tempting to see that, actually maybe the reason we have these sorts of algorithms and we don't have algorithms for things like computational fluid dynamics and things like this, that would maybe also be useful, is because the kinds of people that work on computing, on building new types of computers and so on, are basically physicists and mathematicians and theoretical computer scientists, and they all like these kind of problems. They all encounter them in their own working life, and so they start coming up with algorithms to solve that type of problem. And if you ask about certain other things, like why don't we have an algorithm for computational fluid dynamics or for various geophysics applications or whatever, well, you can go back to the small number of people there are, and then you can think how many of those people also have expertise in algorithms in this other area, and that number is very likely 0. I don't mean it's a small number, I mean it's just literally no people. So we can kind of ask, does this bode well for the future or not? But you can kind of see what should come next. There's some things that come fairly early on in the history of conventional computing that we haven't gotten to yet. We don't really have any quantum data structures. There's like 2 papers on this, or something like this. And really, you need data structures to build better algorithms. Otherwise, you're reinventing the wheel every time. We also need abstraction. We need some way of people being able to program a quantum computer without having to fully understand all of the tricks that are used to build quantum algorithms, because if you need to understand all of that, that's several years of study right there. So we need to start developing these techniques that have come on fairly early on in the history of conventional computing, and we need to start doing the same for quantum computing. There are also innovations on the hardware side that could make things easier. A lot of the machine learning algorithms and the fast linear algebra algorithms that I mentioned rely on having some kind of quantum variant of RAM. So they kind of work in this RAM model where you have some kind of pointer that points to a location in memory, and it can read out that location of memory into some other register in the processor. But what makes it quantum is that the pointer register can be in a superposition. So when it reads out a location in memory, the memory doesn't change, it doesn't become a general quantum state, but the register it's reading into can now be in some general quantum state that's maybe entangled with the pointer register. And we don't have that yet. At the moment, the architectures people are pursuing for quantum processors, basically everything's active, there's no passive RAM or anything like that. We don't have a kind of von Neumann architecture or anything like that. And we kind of need to start getting into a position where we have things like this kind of quantum random access memory if we want to have some of these fast linear algebra algorithms and things like that. So there's some innovations on the hardware front that can also make a difference. There's another realm of applications as well. So if you have 2 quantum computers, you can put them together, you can connect them so that they can transfer quantum states from one to the other. And if you do this, you get a whole bunch of new applications. You can do a couple of things in security, so I can mention a couple of them, but you can also compute certain distributed functions much more efficiently than you could otherwise. So you can compute things with far less bandwidth usage than you would otherwise be able to do. So some of the things we've kind of worked on in this area before is like secure delegation. So if you have a user that wants to delegate a computation to a remote quantum computer, they're able to do that very efficiently. And you can also do things like verify that a quantum computer is doing the computation you desire. So in this kind of networked setting, you get a bunch more applications as well. And there's a lot of work in that process. So there's already this Quantum Internet Alliance, so you start seeing efforts to build quantum networks for communication and also have some processing component within them. Okay, so I'm going to finish here, but I just wanted to show you the timeline of kind of what came next for conventional computing to give you an idea of where we might be. So if we're in the 1940s, what does the future hold? So 1937, the Turing machine was introduced. We've got that already. We have a quantum model of computation called quantum Turing machine. quantum Turing machines. And actually, we use a different model called the quantum circuit model. But there's this we can tick off our list. But these we can't. We don't have any high-level programming languages. So the way you program a quantum computer at the moment is you program your own conventional computer in maybe a high-level language like Python or F# if you're using Microsoft's Q# thing. So you can program your conventional computer that's controlling the quantum computer, the quantum processor, in a high-level language. But in terms of the quantum processor itself, you're sending basically assembly language instructions. You're saying, now do this gate, now do that gate. And that's not necessarily what you want if you want to be able to build complex software. It also means that there is no abstraction at all. You are very much rooted in the hardware. So something you would hope for is maybe that we can take off high-level languages. We also haven't seen stored program quantum computers. At the moment, the paradigm everyone's working in is treating a quantum processor as a coprocessor that is controlled by a conventional computer that stores the program. However, there's a bunch of extra things you can do if you go to a stored program model where your quantum computer is reading a program that's stored on it. There's a bunch of things you can do with pointers that make you able to do certain things more efficiently than otherwise. And you can kind of tick off the list. We haven't seen error correction yet. We haven't really seen optimizing compilers, and we haven't started seeing internetworks yet and things like this. We've seen maybe some short-scale demonstrations of quantum networks. But that's pretty much it. So it kind of gives us maybe a plan of what the future or the not-too-distant future might hold for quantum computing. So I'll leave it there. I guess we move on to the panel discussion now, and I'll hand you back to Jenny. Thanks.
Okay, thank you, Joe. So everyone is now an expert in quantum computing. So we are going to move on to a panel discussion. We keep Joe here, and we've got three other brilliant speakers who are here to take your questions tonight. They have decades of experience together in quantum technologies and some classical technologies too. And we have perspectives from hardware and software, and they're also from startups and the mighty IBM, so you've got a whole range of backgrounds here. I just want to share a little bit about the questions. So we're going to take questions two ways, both from the floor, or if you prefer, there's an online app that you can use. So I think the details from that will be up shortly. So you can send questions in either way. We also have people watching online, so if anyone wants to send a question, they can use Slido to do that. So now let me introduce all the experts, and I invite them to come up and take a seat. So first we have Tommaso De Maria. He's co-founder and CEO of Entropica Labs. We have Rainer Dumke, a principal investigator at the Center for Quantum Technologies and co-founder of Innovators Q. And last but not least, we have Christian Retsch, who is vice president and CTO of IBM Systems in Asia Pacific, and Christian is also an IBM Quantum ambassador. So, welcome. Okay, I have given a brief introduction, but to start off, I would like to ask each of you to introduce yourselves a little bit more. Joe, we'll start with Tommaso. You've already introduced yourself.
Thank you. Thank you, Jenny. So, hello, everyone. My name is Tommaso. I'm a physicist by education, so I study physics in Italy. And the funny thing is that I studied environmental physics. And I became really interested in quantum computing when, with my professor at the time during my master's, we realized that there are very hard equations that are really difficult to solve with conventional computers. This was like more than 10 years ago. And then the idea that we had at the time is whether these quantum computers that at the time were still not maybe as known as they are today could help in solving such equations. So I completely switched field. I moved to quantum computing, and then I also moved to Australia to do a PhD at Macquarie University. In 2014, I moved to Singapore to work together with Joe at SUTD as a postdoc fellow. And at the beginning of this year, I quit my academic position, and together with Yuan Muro, who's sitting behind there with a purple shirt, we joined an incubator here in Singapore called Entrepreneur First that helps people who come from academia to bring their ideas to life. So we founded a company called Entropica Labs, and the idea at Entropica is to really leverage the power of quantum computing to tackle hard problems in molecular biology, and in particular in genomics, with the idea of getting a little closer to precision medicine. Yeah, so thank you.
Okay. Hi, my name is Ryan Damke. I'm, as similar to Joe, a principal investigator at the Center for Quantum Technology in Singapore, and at the same time faculty at NTU over at the other side of the island. I've actually started, let's say, working in this area when I was back in Germany during my PhD. Actually, there we have tried to realize, let's say, architectures for based on neutral atoms for use in quantum computation and quantum information. Later on, then, actually, I went over to NIST, US, Gaithersburg, and worked there on molecular systems. So I switched a little bit the field, or the let's say the physical system in this case, and then after 2 years working in there, I went then back to Germany at the Max Planck Institute for Light in Erlangen and worked on ion traps and optical clocks. One can actually say, if you look at, let's say, quantum computing with ions, it's just a bunch of connected optical clocks. 12 years ago, I've come to Singapore and started actually research and projects on developing quantum technology, especially for confirmation processing, based on atomic and superconducting systems, with a small but quite brilliant team. So some of them are actually sitting behind there, also working in my lab. Okay, I think that's roughly all. And, sorry, one more thing. And more recently, I have started with a few colleagues of mine, a startup company, Innovators Q, where we actually poised to actually build hardware or build actually a scalable quantum computer.
So my name is Christian Retsch. I'm a quantum ambassador, and I'm with IBM here in Singapore. I'm responsible for Asia Pacific for all the technical teams in the systems division. And I'm also the CTO for the systems division in Asia Pacific. Now, I'm a long-time IBMer, so I have 30 years of experience in IBM. And I came into IBM after I studied engineering at the Austrian university, so you can hear from my accent maybe that I'm coming from Austria. And I joined IBM because I realized after my engineering degree, first of all, that was a great company to join, but also how much everything was moving. So I needed to earn some money at the university, and I started to program computers. That got me into computing while I was continuing with my engineering education and my engineering degree. And I thought computing is moving so fast. I was thinking about switching from engineering into computing as a study, to do a computing degree or a computer science degree. But then I thought computing is moving so fast, I will anyhow stick with computing because I got so excited about it, but I will apply it to engineering, and I will therefore do my engineering degree, continue to earn money with programming, and that brought me into IBM. And essentially that story, as it started, continued throughout my whole life. So there is not a single day where I do not learn in IBM and where I do not enjoy doing new things. So I also was having a career that was about building new initiatives, launching new projects, leading businesses, kinds of startups within IBM. And finally, I ended up, after having worked in Central Eastern Europe, Russia, Middle East, Africa. I was based in China. I'm in Singapore, which is one of the most vibrant places to be, as you can also see from this event. And I'm a quantum ambassador and have the role that I explained earlier, and I look very much forward to the discussion and sharing the views that we have and the actual work that we do in the field of quantum computing. Thank you.
Thank you, everybody. So please get ready with your questions. I'm just going to start us off by asking if each of the panelists can talk a little bit about where they see things going in the next few years. So we heard from Joe that some kind of noisy, small quantum computers already exist. But in the next 5 to 10 years, what is it that you hope to see?
Okay, so at least for me, I think you'll probably get different answers from each of the people here. I think the way things are going, we'll probably see at least some suggestion that this threshold for quantum computational supremacy that I alluded to in my talk has been crossed maybe within the next 12 to 18 months, something like that. There were a number of other things on there that are important milestones to having a large-scale quantum computer. So crossing that threshold only shows that for some random problems, the quantum processor outperforms a conventional computer. It doesn't yet mean that it's useful for anything. We don't know if it solves a useful algorithm at that point. My understanding is that you need to get, at the moment for the algorithms we have, you start to see applications at around 200 qubits when the level of noise is really quite low. So there will be a gap between crossing that threshold, the threshold for just the device being hard to simulate, and it being useful. But still, that's something that we might hope to see in the next couple of years. On the technical side, we'd maybe also hope to see some demonstrations of error correction and maybe fault tolerance. So that will be quite a big thing to be able to demonstrate. And then, as you move out towards 10 years, hopefully we would start to see some demonstrations of things like quantum random access memory and things like that that are quite important for being able to solve certain types of problems, and also start to see fault tolerance. So start to seeing devices being built that can store quantum information for a very long time and that can also process in an almost noiseless way. Now, when we do that, there's a large overhead. So you're encoding 1 qubit into maybe 100 or 1,000 physical qubits. And so you need to have devices that have really large numbers of qubits before we see that. So in order to have this kind of almost perfect noiseless quantum computer, we really need to progress quite far. So that's out, maybe that might be out beyond the 10-year horizon. That might be further into the future. But hopefully we would start to see the first kind of implementations of fault tolerance and things like that before then.
So Joe covered the technical milestones extremely well. So I'll try to answer this question in a slightly different way. So what I hope to see in the next 5 to 10 years is really to take the whole field of quantum computing, if you like, away from this scientific endeavor, which is really fascinating, but it puts it a little distant from the business side of things. So if we really want to see this technology growing and evolving, there's a real need, I believe, for companies to understand how useful or how completely game-changing quantum computing can be. And this requires an effort from our side, so from academia, for people who come out of academia like us, to really go out there and talk to people so that we can understand what their problems are, so that we can also go back to the companies that are actually building quantum computers, that are building software, and tell them exactly what the needs are. Because it's very difficult for a new technology, it doesn't matter how fascinating it is, to actually go, to become part of the real world if there is no real application for that, or at least if there is no clear application. So what I would like to see in the next 5 to 10 years is a global effort from the community to go out there, to reach to people, to understand what they need, so that we can start closing the gap between, if you like, quantum and industries or real world applications.
So it's a pretty hard question to actually look into the future, I assume. Maybe I will answer this a little bit on the hardware side. So I trust, let's say, that within the next 2 years or so, we see quite a few systems or physical platforms, or at least 2 physical platforms, which actually will operate qubits in the range of, let's say, 30 to 50 qubits, roughly, with decently low error rates. Going then actually to higher qubit numbers, to let's say about 100 qubits with small error rates. Actually, this is not really possible with using the current technology and just scaling it up. There has to be some changes in this devices. For instance, if you're looking at ion traps, for example, it's very hard to store, let's say, 100 ions in a single ion trap. So there actually one has to think about crosstalk between this ion trap, similar to superconducting devices. So having, let's say, hundreds of qubits on a single wafer, you will see some crosstalks between this wafers. So there has to be some technical developments or advantages. And we actually also roughly know what to do. So we have an idea of, let's say, how to process the systems or increase them, but it takes some engineering and challenges. And these are also some of the steps Joe was mentioning later on, where you see this doubling of the qubit number. So if you tackle one of these technical challenges, you can then increase your qubit number significantly with low enough error rates. What I assume will actually happen in about 10 years' time is maybe actually that we not only have a single physical realization of a quantum computer, but let's say one or two platforms where a system is realized. And these platforms will have, let's say, distinct advantages over, let's say, the other platforms. For instance, ion traps have, let's say, certain advantages over superconductors, and superconducting quantum computers have advantages over ion traps. And the combination of the two would probably be a help to actually tackle future problems.
So I actually expect that we will get from a quantum ready status that we have now into a quantum advantage status within the next 5 years. Quantum ready is what we said we have achieved when 2 years back the first physical quantum computers were available. So IBM made the physical quantum computers, when we announced them, accessible to everybody over the cloud. So that was for the first time where we said we're quantum ready because you could really test the physical machine, a real computer, not just in theory, think about it, do algorithms, prove that they will work, but without running them on a real system. Now, yes, the quantum systems that we have now, quantum ready, are still relatively small. They also are noisy systems, as we call it, so there are errors in crosstalk between the chips, etc. But they are physical machines that already are proving very, very useful insights. For example, IBM Research could demonstrate that we could simulate beryllium hydrate, a molecule, and see the state, the energy state of the molecule. And that is not a big molecule, so you can do it on the medium-sized noisy system that we have now, but you could also prove, simulating the same molecule on a traditional computer, that a quantum computer is really delivering the right and good results very, very efficiently. So quantum advantage is when a quantum computer gets strong enough, has enough qubits, error correction, everything is needed, so that a simulation of a molecule can be done in a quantum computer faster, cheaper, or maybe only be done on a quantum computer because it's such a big molecule that you cannot ever simulate it again or sometime in the future on a traditional computer for the reasons that Joe explained initially. So I strongly believe that with the quantum-ready state that we have now, with the worldwide collaboration that we have opened up with startups, with research, with universities, in the IBM Quantum Experience Program, where everybody can access these systems, or in the quantum network, where we make the largest quantum systems that we have up and running accessible for industry partners and large universities, I believe that with everything that's going on, we are getting into the quantum advantage stage within the next 5 years for specific use cases. And that is what you, I believe, Joe, call quantum supremacy. So it's pretty much a similar term addressing the same thing. So quantum computer doing things better, or being the only computer to do something that a traditional computer cannot do anymore. That is what we get into in the future, in the near future.
Okay, thank you. So I see some of you are already asking questions through the app. So I'm going to move to one of those and then the floor. So I guess related to this question of what quantum computers can do, we have an anonymous question of, is there an immediate business need that we can solve with this technology? I don't know, Christian, do you want to take this one?
So the immediate business need, I think the most promising field is in chemistry and material science. So if you think about the effort that it takes to find a new medicine and all the research and tests that you need to do with today's methods, if you imagine that with the quantum computer you can actually analyze and simulate how large molecules behave that cannot be simulated on any traditional computer. If you think about the possibilities that this opens up to find new medicines much, much, much faster, or new materials much, much, much faster, that I think are the real promising use cases, the most pressing use cases, because it will benefit all of us. If we can get access to new antibiotics that can be found and where are no resistances yet built up because they are new, if we can simulate it, if we can get to that kind of a level of understanding at a much, much faster speed, then all mankind will succeed and will benefit from it. Another example from daily life, if I would have a battery in my iPhone that would last a week instead of a day because somebody found a new material that builds a much, much stronger battery, that would be of tremendous benefit. And think about a battery that you could use, a new kind of battery for electric vehicles, for maybe electric airplanes, maybe for a new kind of society and how we deal with energy and electricity, connecting households, having maybe a distributed kind of electricity supply with renewable energy feeding into such batteries. That would be another use case that would be very interesting to have. And of course, there are many others that I can't even think of right on the spot, but other people perfectly, I think, already do. And one of the entrepreneurs here for sure have also thoughts.
Yeah, sure, maybe I can add a comment. I think is very fascinating. So these kind of questions were exactly the questions that people would ask when the first classical computers were developed. And it was unclear whether they were useful beyond those applications they were built for. And as Joe showed before on the slides, the first classical computers were really built for physics simulation and for cryptography. The first quantum computers were thought for physics simulation, as the one that you just mentioned, for chemistry or for materials, and for cryptography, breaking RSA. And then, you know, we have the tendency to try to imagine the future looking at what we already know. And again, going back to the slides that Joe showed before, most of the use cases that we have in mind today for quantum computers are pretty much the quantized version of cases that we already understand using classical computers. What I think is really fascinating when it comes to quantum is to try to imagine, at least to get very excited about all the use cases that we have not even thought of. Just like people have not really thought of, you know, what we are actually doing right now with the computers that we have in our hands in the 40s or in the 50s. So even if we don't see why quantum computers are useful today, that of course doesn't mean that they are not going to be extremely useful in the future. And I think the history of classical computers really showed that.
So I guess there's a couple of ways to answer this. One thing you can say is that there's definitely a pressing business need from the point of view of the startups, because we probably have a hard time raising funding if people weren't working on the hardware. But if you think about it in a more serious way, there's a couple of things that can help. That quantum computers can help with. I think myself, so it's very widely recognized that chemistry is an application where this is important, and maybe also material science. But if I was to bet myself, I would actually think a really early use for quantum computers is as a mathematics coprocessor. You can do a lot of mathematical calculations of things that people care about, particularly people that are trying to build better quantum computers, things that they care about using a quantum processor than you can otherwise. It's very hard for us to simulate large devices. No matter how large a computer we have, we can't simulate beyond about 50 qubits. And if we're trying to develop algorithms, if we're trying to do anything like that, this blocks us from trying heuristics. So all of the algorithms you try, you then need to go and prove that they work. And that is incredibly time consuming. And having a test bed to be able to implement them beyond a handful of qubits in simulation, that's really going to be important. So it's going to help us get further along with quantum processing. By having rudimentary quantum processors, we can get to better quantum processors. But I think in general, the use for them in linear algebra, differential equations, things like this, I think there's a real use case there. The other thing that I would maybe say about this is that I agree completely with Tommaso that this is very similar to early things that were said about the first computers. And actually, at the end of our slide deck, when we go and we try to raise money, I have quotes from the early from early people in the computer industry about the need for the need for conventional computers, and what the total world market is, and various things like this, and this quote that in the future a computer may weigh no more than 1 ton, and all of this thing, okay, the IBM one about there being a world market for 5 computers, that seems to be apocryphal. It doesn't seem to have really happened, but there's a bunch of these quotes that we seem to have forgotten about. So I have a list of these quotes, and I've just inserted in the word quantum in front of all of these things, and I think it's really, really similar, and that we're at a similar stage in the evolution. And it may still be quite a time before we get to a quantum iPhone, but yeah, that might be 70 years off. But I do think we're moving in the right direction.
Okay, thank you. So we have some questions from the audience. I think we would like you to use microphones, so we will pass these around just so that people watching on the live stream can hear you. Okay.
Hi. This is more of a question from the algorithm side of it. But in terms of the actual machine learning algorithms, would you imagine, based on the current direction of quantum computing, that something linear algebra friendly, like say ensemble systems, some of the classic 90s algorithms like Ada boost, stacking, bagging, would be more easier to implement in the near future than, say, something more complex like deep learning or reservoir state computing?
So any of basically any ML algorithm where you're applying it to a large amount of data, there's a problem with seeing it implemented in the near term on quantum computers. And that problem is really simple. It's just the input-output problem. Although we have algorithms that run in logarithmic time for clustering, and we have them for matrix inversion and things like this, or in polylogarithmic time in the matrix size for sparse systems at least, this is potentially better than you can do on any conventional computer by a very large margin. The problem is, in order to read in the data into your quantum device, if you're reading it in sequentially, it still takes a linear amount of time. And if you want to get away from that, what you need is some kind of quantum random access memory. And that's kind of the hardware stuff that I mentioned in my talk that we don't have. So we know basically what we need. It's just a quantum version of RAM, but we don't have it yet. And that's probably not likely to be available for early applications. So the first applications probably won't be ML because the bottleneck of reading in the data creates a problem. People are trying different machine learning models. One of my PhD students who's just finished had quite a nice paper on doing Bayesian deep learning. And one of the reasons that he goes this way is because you do it all as a single giant matrix inversion step. And the matrix is way too large to invert on a conventional computer, so you end up making some kind of hack to try to work out approximately what the inverse should be on a conventional computer. But because on a quantum computer you're only using logarithmic time, inverting that matrix becomes potentially really easy. So taking this thing that would take it to some kind of cubic trading time or something like that, and turning it into this polylogarithmic matrix inversion step, that seems very appealing. And there's a lot of areas you can apply this in. It's been applied for support vector machines. We did it for some Gaussian process regression and things like that. It's been used for a whole bunch of different areas. So it's a fairly well-established technique at this point, and it's being used in a whole range of machine learning problems. But again, you find that the people that get into this, they're not, either they come from machine learning and they don't have so much of a quantum background, but much more often they're coming through from the physics or quantum side, and they're kind of picking up the machine learning as they go along, and that also impacts things. So you have this this issue where the kind of intersection of expertise can sometimes be a little smaller than you would like.
So we have seen that in some areas of machine learning there is actually very promising possibilities using a quantum computer. And I saw some reports on classification and finding patterns in images, etc., that seem to be very promising to do on a quantum computer. So if you're interested, I can connect you to the people who know that in more depth, and we can find out where this is heading. But I think it goes back to what was said earlier by Tommaso, which is there's so much as a possibility out there which is unknown, that we really are very, very curious and also excited about finding out. And as it was mentioned, who would have thought when IBM, Thomas Watson Jr., back when the computers were invented, said there is a market for five computers, that actually we all will have a computer in our pocket, right? And that we have new business models that become very viable, like calling a taxi with your iPhone, and or having Airbnb and whatever you can think of. So I think we're at the same stage with quantum computing, that there is a huge space that is wide, wide, wide open if we just decide to spend time and go after it.
Maybe I can just add a quick note on this question. So I really like to think of quantum computers as sampling machines. So one thing that quantum computers can do that is very hard to do on classical machines is to sample from certain distributions that are intrinsically difficult to reproduce on classical devices. So if you can come up with a machine learning or with an algorithm that requires sampling as part of the procedure, and you can use even a small noisy quantum computer to do the sampling part, and everything else still remains on the classical computer, then you might be able to see an advantage, in a reasonably short time from now.
Do you have a specific example?
So people are, there are specific examples. So people are looking, for example, at quantum Boltzmann machines. Again, it remains a little difficult today to understand what size you need for a quantum computer. Then there is the question of what error rates are required to get something meaningful or something beyond classical computers. But yes, people are certainly looking at this kind of techniques. There's many examples, and maybe we can discuss more in depth later. Yeah.
So I have a two-part question, it's John. First part is around, I think one of the applications was for being able to break elliptic curve cryptography using a quantum computer. I think that a lot of people have been looking at that as potentially as an application, which unfortunately I guess is something that is probably coming. I'm curious as to how many qubits and how far out you think that is. And the second part to my question is I saw a lot of Western companies, we have IBM, Google, et cetera, listed on the slide. I believe that China is also doing research in quantum computing, and I'm curious how their progress compares to the companies we've been looking at here.
So the first part of the question is about cryptography, right? So, and where we're going. So maybe if you want to revert to that. But essentially, yes, quantum computers and quantum processors, we know from algorithms that have already been found that once we can run them on big enough machines, they can crack encryption that we have today. So encrypted data can be read with a quantum computer that cannot be read with traditional computers trying to get through the encryption, right? Now, we believe that we are years away from having a quantum computer that has the necessary fault tolerance and also at the same time the necessary number of qubits, so that these algorithms like Shor's algorithm can really be applied to get through the encryption that we have today and read encrypted data that should in reality stay encrypted. Now, at the same time, nobody knows how many years it will take. We believe for some encrypted data it will be decades, so it's not really near term. There are some other predictions that progress might be faster. It will only be 7 or 10 years away until encrypted data will be possible to be decrypted with a quantum computer. Now, the really important message here is that the problem, so to speak, is understood. Everybody knows the clock is ticking. There's quite some time left, but as I said, nobody knows the exact point in time. And there's quite a lot of work happening already today to introduce encryption techniques that are quantum safe. And by the way, IBM is also doing quite a lot of work together with some standardization institutions in the US and other places, so that data that is encrypted today and is not safe can be put into a new encryption scheme that will be safe for the long term before actually the quantum computers are at a stage where we could decrypt today's encrypted data. So it's a task for all of us to do this, and it's being done. Now, for the second part of the question, could you briefly remind me what it was? China, yeah, sorry. So yes, there is an enormous amount of money flowing into quantum technologies. There's an investment in the European Union. There's a bill that is just passing through the houses in the US to put more than $1 billion into a quantum initiative. And China is putting a ton of money into quantum research. And we also know that Alibaba is investing into quantum technologies. We in IBM, we focus on advancing the technologies that we have, and our approach is to really give access to the technology at various levels. So we publish every progress that we make. Now, you can search the web and you will find announcements, but we focus really on providing the real progress that we have in terms of proof, down to error rates that our systems have today, qubits that they have today, and also feedback, what people do with it. So I cannot really comment on how far other competitors are with their systems, but I think it is best if you simply go to the internet and compare what you find in terms of, on one side, announcements, but most of all, real examples of use cases, what has really been done with these systems, and what is being published in terms of the characteristics of these systems. So basically, marketing versus a little bit of reality.
Yeah, sure. So in terms of the crypto, the various crypto systems that are vulnerable, we know RSA is vulnerable. We know that Diffie-Hellman and LGAML and other discrete log-based systems are also vulnerable, and we know that elliptic curves are vulnerable to quantum attacks. And basically, the attack is essentially the same with all of these. They're all instances of a particular problem that's called the abelian hidden subgroup problem, and there's a general algorithm for this, a general quantum algorithm for this. In terms of the number of qubits you need, the number of logical qubits, if everything in your device was perfect, the number of logical qubits you'd need to decrypt RSA is about 6,000. Well, it depends on the key length. So take your key length, multiply it by 3. That's the number of qubits you need in order to break RSA. For elliptic curves, it turns out it's smaller. So there was a study on this fairly recently from Microsoft, I think, that had estimates for the size for attacks on elliptic curve crypto systems, although I don't remember exactly the numbers. An important thing to factor in, though, is that this is talking about a perfect quantum computer. So it's a quantum computer where you do not have any issues of errors occurring during the processing. Everything can be done perfectly precisely. And that is not the situation with the devices we have now, and it's not likely to be the situation with the devices we have for a long time to come. The devices we have are noisy. And in order to attack the crypto system with a noisy device, you need to suppress the errors as they occur. And the amount of resources you need to put into that is very, very sensitive to the level of the noise. If the noise, if you get an error like 1 time in a billion, then you don't need much error correction, right? So if you have like if you have 9 nines of accuracy or something like that, don't worry too much about it. You can do some very minor error correction and you'll be fine. But that's not the situation we're in. If you have a look at the IBM system, for example, you can log in, you can see the calibration data for it, and it will give you the error rate per 2-qubit gate and per single qubit gate. And that error rate for the 2-qubit gates at the moment seems to range from about 2% to about 8%, which is pretty high. Right? That's too high to error correct. Now, that's not the best gate in the system, and it depends what system you look at, but we're going to need error correction. And if we're very close to the threshold for error correction, then you need to encode in very large systems. So you take your 1 qubit and you encode it into thousands or millions of qubits. So every 1 qubit in your device, you now need to multiply by 1,000 or 10,000 or a million. If your error rate drops down significantly, though, if it drops from just below 1% to just below 0.1%, that has a big impact. And if it drops another factor of 10, then it has a huge impact. And so as the error rate comes down, it really significantly affects the overhead and the size of device you need. And because of that, it's very hard to come by very concrete numbers for how close that is. Any advance we have that makes the qubits better, that's gonna really affect things. In terms of the other part of the question about what's going on in China, I guess a number of our colleagues have moved into Chinese firms, but I don't know so much about what they're doing at the moment. But they seem to be hiring good people. In terms of cryptography, on the other hand, so quantum key distribution, where you're using quantum mechanics to build up secure links to communicate over, there's a collaboration between Alibaba and the University of Science and Technology in China, and they're absolutely world leaders in terms of range for quantum key distribution. So they've been doing Earth to low Earth orbit and stuff like that, and that's been really impressive over the last couple of years.
Okay, we take a question at the back.
So Joe, earlier you were talking about like polylogarithmic time, and I've heard you talk about classes of problems. So I was kind of wondering, there's a whole like P versus NP and NP hard and different kinds of problems. Yep. Does quantum computation kind of reshape how we classify problems, or at least impact?
We have another class. We call it BQP. So BQP is like quantum P. It's the quantum version of P. So instead of calling it QP, we call it BQP because we allow for error. So B means bounded error. So it means the algorithm should give you the right answer with high probability. And this is like a classical class. So instead of P, which is what you can solve in a deterministic computer in polynomial time, for any one problem, you'll either solve it or not solve it, right? But if you have the ability to flip coins, you have the ability to generate randomness, then sometimes you can make more efficient algorithms. And that has its own class. That's called BPP. So it's bounded error probabilistic polynomial time. And so BQP is like the quantum version of this. We don't know where it sits in relation to P and NP. We have some evidence, and we have evidence that if you could efficiently simulate a quantum computer, then it would have implications for classical complexity classes, that perhaps it would cause collapse in the polynomial hierarchy. But it's not at the level of P equaling NP. It's higher up in the polynomial hierarchy. Sorry, I'm not going to be able to explain the polynomial hierarchy, but it's basically a hierarchy of classes of this form.
Hello, thank you. IBM, you seem to be the earliest lead catalyst in the quantum computing. I know it's the 1970s, late 1970s, then 80s. But then the problem is that the missing link of mass adoption is not forthcoming, and it was overtaken by cloud computing, non-players like Amazon and Google. It was very devastating because you guys are the early pioneers, Oracle, Sun Microsystem, but we were waiting and waiting and waiting for sensibility of mass adoption capability, and offering is not forthcoming then, even until now. The future ready have been talked about decades ago. So the question here is, how realistic are you guys? Because you know why? Whether quantum, Q1, Q4, or you say QG, gear 1, gear 2, gear 3, gear 4, is still not forthcoming. So what do you think that realistically, because I noticed when you talk about collaboration with the startup, well, you partner with iSpace of Japan. The Moon experimentation and the Moon elementum. But that is a distant, planet orientation. Here the question down to Earth, we're still not forthcoming from IBM. Do you really have something that you can offer, particularly the business model offering that you think for mass consumption, which is long overdue? Thanks a lot.
Yeah, so first of all, thank you, because I think what you say is that the many technologies have been invented by IBM, and not only us took advantage of it, others also took advantage of it. But still, we see ourselves clearly in the lead in terms of quantum, because we were the first ones ever to put a system on the cloud, and a quantum system on the cloud, make it accessible to everybody. Quantum, as we said, is in the quantum ready state, so everybody, startups, universities, students, can work with it, and they do. We have more than 100,000 users, active users on our quantum systems already today through the cloud. We have way over 100 papers, research papers that were published using our quantum computers without us being involved. We have, I don't know how many schools and other institutions using our quantum computers. So we clearly are focusing on supporting mass adoption and also creating possibilities for an ecosystem and for startups to take advantage of it. Another proof point why we believe that we are on a very, very good path, besides the large numbers of users, is that the quantum software development environment, QuizKit, that we developed, is actually available through GitHub. And we made it accessible through high-level languages like Python, etc., that people can use. One element within the software development kit is a library where quantum algorithms can be accessed and called, and we have started to populate this environment with algorithms, starting with chemistry, because, as I said, we believe that that is one of the very promising use cases, and we are adding additional algorithms for machine learning and other use cases. And that is really, really important for mass adoption, because we strongly believe not everybody needs to go and have a quantum physics degree to work with a quantum computer. Today, we all use classical computers, but we also have no degree in how to build the chip. And it's the same thing. So we are very, very much aware that we are leading right now, that we need to enable an ecosystem to work with our systems, that we need to give access, that we need to have open source SDKs, which we have, that we also, within the software stack that we provide, we have APIs on different levels, even down into the chips. You can, with an API, take control. You can even get into the microwave control that works with the qubits, if you're interested to go to that level. So I believe we are on a very different and very, very good path for quantum compared to some other technologies that we invented in the past, and where maybe others benefited from our inventions but brought our technology for them to mass adoption more than we actually did. So I hope I could give you an overview, because I'm actually very, very excited of where we are and where we're heading. And happy to talk also later one-on-one.
Yeah, we are coming close to the end of time, so I think we're going to squeeze in one quick question with quick answers, and then we'll have a little more time to talk to our speakers and to each other.
Yeah, probably this will be a quick question, because I think it might be a stupid question. So what I picked up from Professor Joe's question was that if you transmit, let's say, 300 qubits, right, it's actually equivalent to 2 raised to 300 bits, right, when you compare it to its analog equivalent. So my question is, if I transmit 300 bits, probably the signal-to-noise ratio requirement is very low. But then if you transmit information with 2 raised to 300, which is actually a huge number, is it safe to say that the equivalent signal-to-noise ratio scales at the same factor? And if yes, it seems like a very huge problem to solve.
Maybe I start with this, since I have a microphone. So what John was mentioned was right, that if you have a single qubit, depending actually on the physical realization of the qubit, you have intrinsic noise. And there are, let's say, certain types of physical realization which have less noise than other types of physical realizations. Examples are, for instance, superconducting qubits, which have very fast gate operation times, gigahertz, coherence times in range of microseconds, 20, if you have isolated qubits in range of 100 microseconds. For instance, for atoms, ions, right, you can have coherence times up to hundreds of milliseconds to maybe up to seconds if you use an ensemble of atoms. However, the interaction times are usually in the range of megahertz, right? The ratio between the two, right, gives you sort of how many gate operations I can actually do. The other very important number is actually how good are these gate operations. And they actually also depends on the physical system you are using. For instance, the gate operations you can do, for instance, with ion traps or with ions, are much, much more pristine than you can do with superconductors. However, they are much slower. So you can do, in principle, more operations on a superconducting device than you can do on an ion trap device. But you would need not so many protecting qubits for an ion trap-based quantum computer than a superconducting quantum computer. There's another, actually, physical realization of quantum computers, the topological quantum computers, where actually there the error rates probably will get way, way much more smaller than they are realizable with any other type of quantum system we actually right now know. Because there actually the, let's say, state is not really, or the state of the qubit is not really encoded into an energy state. Is actually encoded into the topology of the qubit itself. For instance, you can think about you have a string without a knot and a string with a knot, right? The string with a knot is your 1, the string without a knot is a 0. And you can do anything to the string, you won't change the topology of the string, right? So there you would actually, if you can realize a quantum computer based on topology, this would be actually intrinsic, insensitive to noise. And that's actually also some companies, Microsoft is actually putting quite some effort into this. And hopefully they're actually working really hard towards that something meaningful will come out of this. So again, so looking, let's say, to say that one qubit equals to, let's say, 300, right, is, I think, not really quite fair to say. One actually has to see in which type of system this is actually done.
Yeah, so I think we're touching on a very important point, and that goes also back to mass adoption, which is how powerful is a real quantum computer. And we have seen that number of qubits was one thing that was mentioned, topology of the chip, the gates, of course, noise levels. So IBM research, because we needed to compare our own quantum computers against each other. So IBM research looked at how can we compare the actual throughput, the real usable capacity that the actual quantum computers that we by now have, several of them, deliver. And we realized that we need to define a metric that is architecture neutral as much as it can be. And we defined, and you can find a research paper on the web, we defined something called quantum volume. And key parameters like the number of qubits, the noise level, the gate connectivity, the qubit topology, the kind of parameters that each by themselves can have a huge influence are brought together into one metric, which we call quantum volume because it's multidimensional, that gives you a number that gives you a feeling for how powerful is a quantum computer. Also, if you go to the web and you want to see the actual effect of noise reduction, you can see that we have one and the same physical computer with different levels of error correction and how much the throughput improved. So we're publishing all this, and as we are going towards mass adoption, metrics, or you could even call it kind of benchmarks like quantum volume, will play a key role so that everybody can understand how to look at the actual real capacity and throughput, or compute power, I should say, not throughput, the compute power of a quantum computer compared to another quantum computer, including our own, because we publish all of that for the existing machines constantly on the web.
I think we're probably going to have to end there. Okay, sorry. Quick.
Sorry, I just, if you don't mind me chipping in, I just wanted to mention that I maybe misspoke. This thing about the qubits, if I have 300 qubits, it's not the same as having 2 to the 300 bits. You can't extract that information out of it. You can only, there's something called Haleva's theorem that says if you have 300 qubits, you're only going to get 300 bits out of it. It turns out the quantum states, although there are a huge number of quantum states you can have, and you need a huge number of real numbers to describe it, you can't extract all of that information, but it's useful in computation. It's not directly useful in communication. It doesn't cut down the amount you need, but so you basically get 1 bit per qubit. But when I talked about these computational distributed functions using less bandwidth, in order to do that, you actually need to come up with quite a clever way of doing it. You don't just get a direct reduction. You need to come up with new algorithms for computing the functions.
Okay. All right, so hopefully we've all extracted some information from all of these presentations. I'm sorry we haven't got to all of your questions. We are hoping to have more of these sessions on quantum computing, so please look out for details of those from SGInnovate, and we will address these next time. For now, I just want to thank SGInnovate again. Thank you all for being here, and thank you for all of our panelists.
Together.